Hello everyone, thanks to everyone for watching this video. My name is Qida. I am an architect and engineer. Today's video is going to introduce the flying buttress and buttress. I am going to give you an overview of what I am covering in today's video. First and all, it is a bit of background to the topic, and then focus on the flying buttress and buttress. As a lateral support system, the flying buttress was developed during the Gothic architecture. The flying buttress is a two-part composite support that features a beam that extends to a massive pier far from the wall, and so provides most of the load-bearing capacity of a traditional buttress, which is engaged with the wall from top to bottom. Thus, the flying buttress is a lighter and more cost-effective architectural structure. In this video, we will study the behavior of the lateral support system. First, we introduce the flyer. Consider the inclined plate band as an idealized model of the flying buttress. Supposing the buttress to sag when the centering is struck, then three hinges will form at IO, IL, and EX. Then broken line shows the approximate position of the line of thrust. At sections IO and IL, the line of thrust passes from the flying buttress into the navel and main buttress, respectively. The immediate problem is the location of the section EX, where the line of thrust just touches the extradors. In this video, Coulomb's method will be used. If the weight per unit horizontal length of the buttress is G, then this figure shows the forces on the complete buttress and those on a portion of the buttress of length X. By moments about IL, we obtain this equation. By moments about EX, we get this expression. Combine the two equations, we have the H expression. Now Coulomb states that the value of X must be such that the value of H is a maximum. Hence, X is equal to half of L. We obtain H and V equation. The same results have been obtained by writing the condition that the line of thrust just touches the extradors at EX. This calculated value of H must always be less than the horizontal component of the volt thrust. The latter must exceed the value G times L squared over 8B if the navel is not to be pushed inwards. Then consider the same flying buttress on which is imposed an increased horizontal thrust H star. It may be shown that for the line of thrust sketched, X squared equal to 2B times H star over G, and the V star shows here. This solution holds for X less than L, and H star less than G times L squared over 2B. For values of H star greater than this, the line of thrust passes straight through the flying buttress, from nave to main buttress, as sketched in this figure. It is clear that since there is no possible mechanism of collapse for the plate band, the value of H star can be increased until the crushing strength of the stone is reached. Passive and active lines of thrust are reproduced in the right-side figure. It shows that the passive line of thrust tends to droop at the head of the flying buttress, near IO, and if the masonry is cut to resist the active thrust line, then some sliding might occur at the head in the passive state. An extra prop to the head of the flying buttress is often provided. This figure shows a passive thrust line for the Great Flying Buttress of Notre Dame in Paris. Next, we will study the traditional buttress. This figure shows a masonry buttress under the vertical load Q and the thrust S to it conveyed by a flyer. The buttress has generally a stocky shape because with its weight has to balance the action of the thrust S. The weight G of the buttress is dominant with respect to the load V. In the next, the limited thrust producing the overturning of the buttress will be obtained. The vertical load applied to the buttress will be the weight G and the vertical load V. The thrust will be considered affected by the lambda. The activating of the overturning mechanism will be accompanied by the formation of a detachment fissure starting from the base of the buttress. Only a part of the weight of the buttress mobilized in the opposition to the collapse. A preliminary analysis is thus required to determine the actual geometry of the detachment crack. Let us consider the load that is had by the thrust lambda s and the vertical load lambda q, starting from the section MN and proceeding downward. The sections of the buttress will gradually crack, and the larger parts of the sections will be ineffective. The element A, B, C, D, shown at the right of the figure, defines a small segment of thickness dy of the effective band of the buttress. Equilibrium of the element A, B, C, D gives this equation. Considering dW equal to g times x times dy, the equation becomes this expression. Derivating the equation with respect to the variable x, we obtain this expression. On the other hand, we have dW over dx equal to gx times dy over dx. Then the differential equation becomes this expression. This condition has to be satisfied for any value of the x, so the second-order differential equation of y is equal to 0. Consequently, dy over dx is constant. It means the detachment feature is rectilinear. Once obtained this result, we can proceed to obtain the collapse multiplier lambda of the thrust s. At the failure, the part OFCAE of the buttress that overturns around the toe O subdivides into two parts, the lower triangular zone OEF and the upper part ACFE. The line EF separates these two zones, whose upper has all sections effective, and the lower, whose sections become gradually more and more ineffective. The section EF defines the passage from the cracked and uncracked sections. The resultant of all the loads acting over the section EF will pass through the core point P of EF. Equilibrium around the point P of the upper part of the buttress gives this equation. The solution of this equation gives the height C of the upper part of the buttress, whose sections are all compressed. Let us set a series of symbols. We have capital G equal to G times B times H, and beta, capital Chi, sigma, zeta. Then we obtain this equation of capital Chi. The rotational equilibrium around the toe of the active part of all the buttress gives this equation. The collapse multiplier is still obtained by substituting Chi equation into this equation of equilibrium. Then we get this expression, from which we obtain the algebraic equation of second degree in lambda s. The new equation shows here. The solution lambda times capital sigma of the equation takes this form. For a particular case, we consider the case Q equal to 0. We can use this equation and have lambda s equal to beta times g over 6. The failure zone is a triangular shape. Therefore, we can use this form to understand the behavior of buttresses. From conclusions, what we learned? The flying buttress is a specific form of buttress composed of an arch that extends from the upper portion of a wall to a pier of great mass, in order to convey the lateral forces that push a wall outwards. A buttress is an architectural structure built against or projecting from a wall which serves to support the wall. Buttresses provide support to act against the lateral forces arising out of the roof structures that lack adequate bracing. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.